Hi guys, it's Mrs. Jackson. In this video I'm going to teach you how to calculate pH during a strong acid-base titration. At any point during a titration, as you are adding acid to a base or base to an acid, you can calculate the theoretical pH of that solution, and this is what we're going to work on in today's video. As we get going, please be sure that you have these items ready. You're going to need to get the information and all the examples down in your notes. You're going to need a calculator. You will need your square of fun, and you're going to need your thinking cap. So have all of those items ready before you proceed with the video. A couple of things that I need you to keep in mind, and this is particularly important today, is that when we hit the equivalence point of a titration, the equivalence point simply means that the moles of acid and the moles of base are equal. It doesn't necessarily mean that the pH is equal to 7. For today's video, we will be looking at strong acid, strong base titrations, and for these reactions at the equivalence point, the pH will be 7. This is the only instance in which you can for certain say that the pH at the equivalence will be 7. If you have a weak, strong combination, weak acid, strong base, or strong base, weak acid, then what you're going to be looking at will be a different pH. Those will be covered in subsequent videos. Another couple of things to keep in mind are formulas that we use all the time. First of all, pH is equal to the negative log of hydrogen ions, and then the equation for molarity. Molarity is moles of solute per liters of solution. We're going to be using those extensively in today's video, so be sure that you are familiar with those. We've used them in class, but be sure that you have those ready. I will not be showing all the work for those, but I will show them as we get started. So have your materials ready, and here we go. We're going to get this done. This isn't hard. It's a little tedious. Just keep very careful track of the numbers that you're using. So for this example, we're going to be calculating the pH after different volumes of our hydrochloric acid have been added to our 50 milliliters of 0.15 molar sodium hydroxide. So in this case, our sodium hydroxide is going to be in the flask, and our hydrochloric acid is going to be added in different increments. So as we begin our first practice problem, we're going to look at the initial solution of our sodium hydroxide solution. So remember that sodium hydroxide is a strong base, and strong bases dissociate 100%. So our sodium hydroxide dissociates fully, giving sodium ions, which are spectators, and it produces hydroxide ions. If I want the pH of this solution, I can take the negative log of 0.1500. The negative log of that value is 0.82, which is my pOH. My pH then is 14 minus 0.82, which means my pH for this practice problem, or this part of the problem, is 13.2. This isn't a new calculation. Okay? This is simply taking the negative log of the ion concentration for your strong species and working your way around your square of fun. Nothing in this is new until we get to part B, which is coming up next. Okay, for part B, we're going to start adding the acid to our base solution. Okay, so when we start adding an acid to the base, we are starting, or we're going to be looking at a chemical reaction. And I've got the reaction equation written right here at the top. Hydrochloric acid, which is a strong acid, is going to react with sodium hydroxide, a strong base, to produce water and sodium chloride. Sodium chloride is referred to as a neutral salt because it is the ionic product of a strong acid, strong base reaction. And remember, we said when the moles of strong acid and the moles of strong base are equal, so at the equivalence point, the pH will be 7. And that means that this salt does nothing to influence the pH. So to get started, a couple of things that you need to remember. First of all, because this is a reaction, we're going to do some stoichiometry. So that means we have to be in the proper unit, and that is the mole unit. So we're going to be utilizing this equation. Molarity is equal to the moles of solute over the liters of solution. And so what I have done is I have taken, for my materials in my equation, I have taken my 50 milliliters. I have 50 milliliters of a 0.150 molar solution, and I have substituted those values into this equation. I substituted in 0.15 for molarity. I converted my 50 milliliters into liters, so 0.50 liters. I substituted those into this equation. To get the moles of base. So when I have 0.15 times 0.050, the value is 7.5 times 10 to the negative third moles of base. I have done the same thing for the acid. I have 0.250 molar hydrochloric acid, and for this part of the problem, I have 4 milliliters of that. So I have done the same thing with molarity and the acid. I have substituted in 0.250 is equal to X over 4 milliliters, but in the unit liters, so 0.004. When I solve then for X, my value is 1 times 10 to the negative third. That's where those values have come from. Nothing new. We've been doing that for a very long time. The next thing, though, that I need you guys to keep in mind is when we're doing stoichiometry, we have to have our balanced equation, and that's why we started with this equation at the top. It is balanced, and it is a 1-to-1 ratio. So when I look at the two values of moles for acid and for base, I have less of the hydrochloric acid, so the hydrochloric acid is going to be my limiting reactant. That means all of this 1 times 10 to the negative third moles is going to be used up. So as this reaction moves forward, I use up 1 times 10 to the negative third moles of my acid, and I use up the same amount of the base. So after the reaction is completed, there is no acid left, and I have remaining 6.5 times 10 to the negative third moles of base. And this is the first part. The next thing that I need to find, ultimately my goal is to find the pH of my solution. Well, keep in mind that pH is the negative log of hydrogen ions, or you can find hydroxide, POH, and work your way around. But pH is always based on concentration. Well, this unit is moles. So again, if I am after a concentration, I'm looking for molarity. So I have to take the moles of my solute, in this case the remaining base, and I'm going to have to divide it by my total solution volume. So to find the molarity of the sodium hydroxide, so my NaOH, I have to take the moles of sodium hydroxide, which are 6.5 times 10 to the negative third, and I divide that by my total solution volume. Well, I had 50 milliliters of the base, and I added 4 milliliters of the acid. So my total volume is 50 plus 4. So I have 54 milliliters. I will convert that into liters because it's the molarity equation. So 0.054 liters is going to be the total solution volume. That means for this calculation, the concentration of my base is 0.1203 molar. So you can see that my concentration decreased. Well, that makes sense. I had a base of concentration 0.150. I added acid to it. So the concentration of the base should go down, and it did. So now I calculate the pH. Remember that this is hydroxide concentration. So I take the negative log of that. The negative log of 0.1203 is 0.92. So my pOH is 0.92. My pH then is 14 minus 0.92, and I wind up with roughly 13.1. Okay, so this is going to be a basic solution. Didn't want that to happen. This is going to be a basic solution because I have sodium hydroxide remaining, so my pH of 13.1 makes sense. Okay. If you got stuck on anything, pause the video, rewind it, and watch it one more time. Okay. For the next step, we need to look at the concentration of sodium hydroxide for part C. So again, we're starting off with some of the same information, but on this particular problem, we now have 29.5 milliliters of the hydrochloric acid. The volume and the concentration of the base in this case are remaining the same. I'm still working with 50 milliliters of my 0.15 molar sodium hydroxide solution, so I still have the same number of moles of base. That has not changed. What I'm doing differently on this one is I have added, instead of 4 milliliters like we did on the last part of the problem, we're now adding 29.5 milliliters of the same acid. So I have an acid of concentration 0.250, and I'm adding 29.5 milliliters. Again, using the molarity equation, I have solved for moles of acid, and I'm starting off with 7.35 times 10 to the negative third moles of my hydrochloric acid. Again, with our chemical equation, we are working with a 1-to-1 ratio. So because I have less moles of acid than I do of the base, my hydrochloric acid is going to remain the limiting reactant on this part of the problem. Because I have hydrochloric acid as my limiting reactant, the definition of limiting reactant part of it is it will be entirely used up. So I'm going to lose all 7.375 times 10 to the negative third moles of acid. And I'm going to use up the same amount of the sodium hydroxide. So I'm going to use up 7.375 times 10 to the negative third moles of the base. So when the reaction is over, all of the acid is gone, and I only have 1.25 times 10 to the negative fourth moles of my base left over. So I've used up almost all of the base. Now you'll notice that I'm not talking about any of this information on the product side. That's because with a strong acid, strong base reaction, this water obviously is not going to impact the pH, but neither will the neutral salt formed by this chemical reaction. This will not always be the case, but it is always true for a strong acid, strong base chemical reaction. The salt produced does not impact the pH. So, trying to figure out what does impact the pH is going to be whatever is left in solution. The acid is gone, so the only thing left in solution is my sodium hydroxide. I just have used up almost all of it. Okay, but I still need to calculate my pH. So for the pH, I'm still going to need a concentration of sodium hydroxide to find the pH. Molarity is moles of my solute over liters of solution. So I'm going to take, for my molarity of the sodium hydroxide, I'm going to take 1.25 times 10 to the negative fourth moles of sodium hydroxide, and I'm going to divide it by my total solution volume. So in this case, my total solution volume is the 50 milliliters of base that I started with, plus the 29.5 milliliters of acid that I added to it. Remember, concentration is moles over liters, so I need the total volume of the solution I have now formed. Okay, 29.5 plus 50 is 79.5 milliliters. In liters, it's 0.0795. When I divide that out to find my new molarity, the new molarity of my base is 1.57 times 10 to the negative third molar concentration. I've really decreased the concentration of my sodium hydroxide by neutralizing it with the hydrochloric acid. Okay, so now to find my pH, I'm going to calculate my pOH first. I take the negative log of 1.57 times 10 to the negative third. That gives me a pOH of 2.8, which is going to give me a pH value of 11.2. Still working on the basic side of 7, right? I still have a basic solution. So when I look at what I have in solution, I still am working with a basic solution. So my pH should be above 7, and indeed that is. Always try to keep in mind, though, when you're looking at your calculations, what you're calculating when you take the negative log. Always keep track of what you have in solution. All right, for the next part, we are looking at the addition now of 30 milliliters of my acid. So I'm still working with the 50 milliliters of 0.150 molar sodium hydroxide. So that calculates to be 7.5 times 10 to the third moles of sodium hydroxide or base. And I have my 0.25 molar hydrochloric acid, and this time I'm adding 30 milliliters. Again, putting that into the molarity equation, molarity of 0.25 times the solution volume of 0.03 liters, remember convert milliliters to liters, that gives me a mole value for the acid of 7.5 times 10 to the negative third. So now you see we've reached a very important point. This is what it looks like when your moles of acid are equal to your moles of base. So at this point, I realize that I have hit the equivalence point, which is incredibly important and very helpful as you're doing the pH for a strong acid, strong base reaction. At the equivalence point for a strong acid, strong base, the pH will be 7. There's no calculation to do because both of these are entirely used up. After the reaction is over, neither of those exist. All I have in solution is water and sodium chloride. Sodium chloride is a neutral salt and has no bearing on the pH, so the equivalence point for this reaction is a pH of 7. Again, if you have questions, be sure you're putting those in your notes to ask when we return to in-person. You can also pause and rewind the video if you need to watch the example again. Now we're going to move on and we're going to solve for part E. Okay, so for part E, things are getting a little interesting. I'm still going to have my 50 milliliters of my 0.15 molar sodium hydroxide, so I still have 7.5 times 10 to the negative third moles of my base, but this time I'm adding 30.5 milliliters of acid. So I'm adding more acid than I did on the last example, and the last example was at equivalence. So this time, when I calculate the moles of acid, I take my molarity of my acid, 0.25, and I am going to calculate the moles of acid by using my molarity equation. So in lieu of molarity, I put in 0.250, and for the volume, I put 0.0305, and my moles of acid will be 7.625 times 10 to the negative third. I'm still working with my 1-to-1 ratio, but in this case, I have more acid than I have base, and my sodium hydroxide has now become my limiting reactant. So now we've changed things up a little bit. Now my sodium hydroxide is the limiting reactant. So I'm going to use up all 7.5 times 10 to the negative third moles of the base, and I'm going to use up the same amount of the acid. So minus 7.5 times 10 to the negative third moles of acid. When it's over, the base is entirely gone, and I am left with 1.25 times 10 to the negative fourth moles of my acid. So now I need to calculate my new concentration of my acid. My molarity of my acid is going to be the moles of acid that remains, 1.25 times 10 to the negative fourth moles, divided by my new solution volume. So my new solution volume is the 50 mils of base plus the 30.5. So that's 80.5 milliliters. Written as liters, that's 0.0805 liters, which gives me a new hydrochloric acid concentration of 1.55 times 10 to the negative third molarity. Because this is hydrochloric acid, I can just take the negative log of 1.55 times 10 to the negative third, and my new pH is going to be 2.81. I would like to take just a minute and point out that we have only added half of a milliliter of the hydrochloric acid, but I went from a pH of 7 at the equivalence point to a pH of 2.81 with just adding 50 milliliters. As always, I want to check my answer at the end. Because I had acid remaining, I'm working with an acidic solution, and my pH of 2.81 makes sense. So now let's make our final calculation. Our final calculation, same concept that we've been working with. When I am looking at my sodium hydroxide, I continue to have that 50 milliliters of 0.150, which gives me the 7.5 times 10 to the negative third moles of base. I have a new volume of acid. I'm adding 40 milliliters of my 0.25 molar hydrochloric acid using the molarity equation to find my moles again. I find that I have 1 times 10 to the negative 2 moles of my hydrochloric acid. When I look at the values and understanding that I have a 1-to-1 ratio, I have significantly less base, so it is still going to be the limiting reactant, which means I'm going to use all of it up. So I use 7.5 times 10 to the negative third moles of the base, and I use up the same amount of acid. So minus 7.5 times 10 to the negative third moles of the acid is used. All of my base is completely gone, and that leaves me with 2.5 times 10 to the negative third moles of my acid. To find my molarity, I take my moles of acid, 2.5 times 10 to the negative third moles of the acid, and I'm going to divide it by my new total volume. My total volume is 50 mils of the base plus 40 mils, so that is 90 milliliters of acid, written as liters, 0.090 liters, for a solution concentration of 0.0278 molar. Because this is a solution of hydrochloric acid, I can take the negative log of 0.0278 to give me my new pH of 1.56. And that is the final calculation for this series of calculations. One thing I'd like to point out though, if we go back and we look at the pHs, so at 40 milliliters, I have a new pH of 1.56. At 30.5 milliliters, I had a pH of 2.81. 30 milliliters was my equivalence point, so that's the big important one. I have a pH of 7. For C, at 29.5 milliliters, my pH was 11.2. At 4 milliliters, the pH was 13.1, and my initial pH was 13.2. One of the things that I want to point out to you is how quickly the pH changed. Within just a 1 milliliter difference, I went from a pH of an 11.2 to a pH of a 2.81. One of the things that we are going to look at will be titration graphs. This is a sample, albeit it doesn't match exactly with the data that we just looked at. This is an example of a strong base being titrated with a strong acid. And you'll notice that my pH starts very, very high. My equivalence point, we're going to learn how to read graphs in a later video. Okay. But I have a pretty steady pH change as I'm adding little bits of acid. And then you have a nearly vertical drop, okay, within just 1 milliliter of change. We're going to learn how to read graphs. Your equivalence point, though, is going to be right here. It's going to be halfway up this curve, or up and down this vertical line. But I want you to see how quickly that changed pHs. Within truly just a matter of a single milliliter, I went from a relatively high pH with my sodium hydroxide to a relatively low pH with just my hydrochloric acid remaining in solution. Thank you guys for listening. I hope you got your notes down, bring questions to class, and I will see you soon. Bye.